Hey guys, Dr. J here, and in this video we're going to talk about downloading and accessing INSAR products, data products from the ASF Data Search Vertex. So you can go to https search.asf.alaska.edu. I'll put the link to this in the notes to this video. And ASF is the Alaska Satellite Facility, and they actually are a NASA, see down here, what's called a NASA DAC. And that basically means that they are a data center for certain NASA data sets that you can access. And so you'll need to sign up for an account, and this is a NASA Earth Data account. So I'm going to go ahead and sign in. So you can see now I'm signed in. And if you don't have an account, you can click on this button here if you're on a desktop computer, and that will take you to the place where you can register and sign up for an account. So you'll need to have an account, but once you have an account, you'll have access to a number of data sets, and these will all be for free. So these are all accessible for free on the ASF website. We're going to, in this demo video, we're going to look at Sentinel-1 data. And what I'm going to show you how to do is to use the ASF data processing, on-demand data processing website to create and download interferograms for a particular area. So we're going to go to an area which I am working on right now, which is actually Central Missouri. We'll look at the St. Louis area, and I can add a bounding box to that area just by drawing. If you need to add an area of interest, you can put that here. You can come up here, click on the bounding box. You can edit that box and delete it and so forth. So I'm just going to draw a bounding box there. I've got the Sentinel-1 data set selected. Notice there are other data sets, such as the Opera Sentinel-1, the ALOS Pulsar datasets, Circe ARIA S1 GunW products. Those are pre-processed interferograms, which are only covering certain areas of the country, but you can check those out. UAV SAR, RadarSat. So some of these other datasets you can check out on your own time. For now, I'm going to just draw my bounding box there. I'm going to select Sentinel-1 dataset. I'm going to come over here to filter. I'm going to filter to just data after 2018. Just to kind of keep myself limited on the amount of data that I'm going to get. File type, I'm going to select single look complex. So if you're doing interferometric processing, you're most likely going to want single look complex data. This is sometimes called raw data, or depending on the type of data set that you look at, this can go by other names. But for Sentinel-1, it's just going to be L1 single look complex data. That's the kind of data that we want. And I don't really care about any of these other parameters. I'm going to go ahead and search. And I've got some results. So here you see I've got 2 different tracks that are actually showing up, 3 different frames in each track. I want to reduce my results down to probably just a single frame. So what I'm going to do is I'm going to zoom in here. I'm going to select this frame, and you can see it will choose a product over here, which is that frame. And so I can look and see, okay, this is now product in path 92 and frame 120. So I'm just going to go back up here to filters and select frame 120 for both frame start and frame end. Now you can see I've got less files showing up. And if I do this, then I should now see, oh, I've still got one other track over here. So I'm going to make sure track 92 is the one that I want. So I'm going to also filter to the track, and that's called path in ASF. So there's path 92. Now I really cut the number of files down, and now you can see I've got just one set of frames. INSAR and SAR data is provided typically as frames. So this area here is essentially one frame, and this is the area that gets a repeated image every time the satellite flies overhead. And those other paths, or tracks as I was calling them, those are other satellite paths. Kind of as it's orbiting the Earth, it's coming back to a slightly different point each time. Those make the different tracks. And then at some point, usually every 12 days or maybe every 24 days, in some cases even every 6 days, it actually comes back to the same track. And so these different tracks go all around the world. This particular track is going to get hit every 12 days or every 24 days. In fact, we can look at the dates over here on these products, and we've got July 2nd, June 20th. So this looks like it's hitting this spot every 12 days. Here's June 8th. Yep, so 12-day repeat time for this particular track. We can look at the metadata for this particular frame that's selected here. Here's the start time, the stop time. Looks like it's got the older frames on top, which is fine. Path 92, frame 120. It's the ascending flight direction, so the satellite is flying from south to north, and it's always looking to the right for Sentinel-1. So it's flying from south to north, looking to the right, and so that's going to be important when we think about what deformation we observe and what direction that's happening. Polarization is the polarization of the data. We're not going to talk about that too much. It's useful for other things, and there's some videos posted that talk about that from NASA. Absolute orbit, PGE version, that's not going to matter for us. So this is essentially the data that we want. Now, the INSAR data by itself that's provided directly from ASF, this is, as I mentioned, single look complex images. So we've selected single look complex images as our data type. But what we actually need to do in SAR is interferograms. And so what we're going to do is click on this SBAS button, and SBAS stands for Small Baseline Subset. And what we're going to be able to do is actually select a number of interferograms by using the ASF SBAS tool. And you can see here already that they've got some interferograms filled in. So what this is it takes the frame that we've asked for, and it actually starts generating interferograms. And those are listed over here on the left. So you can see already 407 pairs have been put in there. There are, remember for INSAR, an interferogram is the difference in phase between two dates. So each one of these dots represents a single acquisition, and there's two parameters here. Each dot has an acquisition date, so there's date on the x-axis, and then there's what's called this perpendicular baseline, which is the difference in the satellite position from one acquisition to the next in the look perpendicular direction. So this just means that if the satellite is flying along like this, south to north, put this down. If the satellite's flying along like this from south to north, it's looking to the right. So the right is, it's looking from the satellite down to the ground to the right. The B perp, or perpendicular baseline, is the distance out of that look direction that the satellite is each time it takes an image. So essentially, the satellite flies around one time, takes an image, it comes around again. It's not exactly in the same spot. It might be, as you can see here, it might be up to, let's say, 450 meters off of the location where it originally took the first image. So as the satellite is orbiting, each time it's coming back to a slightly different location, but sometimes very similar locations, and that's what this B perpendicular is. Now, one interesting thing to note here is that it looks like the satellite is actually kind of drifting out of its proper orbit, and this is something which happens when you have when the satellite is losing its ability to control its orbit. So maybe the thrusters are going bad or something. So this will be an interesting thing to see how it changes in the future as this kind of goes on. At any rate, so we've got our acquisitions are these dots. Our interferograms are the blue lines. So if we select a particular interferogram that is showing up over here, this is a particular interferogram which is using these two dates. So you can actually see here in this center column what are the two SLCs, the two single look complex images that are being used to construct this interferogram. Now, the interferogram hasn't actually been made yet, but this is the pair that would be used to create this particular interferogram. And so what we're going to do is we're going to use this tool, and we're going to adjust some of these parameters here in order to get some interferograms and be able to download those and use them for our time series processing. These are interferograms just like the interferograms that you might access from the ARIA project or from another INSAR processing software. So we can use those interferograms in the exact same way. So what I'm going to do to start with is I'm going to increase the time to 36 days, and that will allow us to have more connections. You see here now, many of these dots are connected to several other dots now, and we shouldn't have any gaps between dots. We don't want to have any gaps in between acquisitions. Otherwise, that's going to make it difficult to do our time series analysis. the other thing we're going to do is I'm going to change the date range for SBAS. I see I've got a lot of interferograms going on here. So I'm going to take just probably 2 years of data. I'm going to start in 2022, and I'll take everything up to the present. Or maybe what I'll do is I'll just take everything up to 2024, and that way I'll miss some of this kind of weird drifting that's going on here in 2024. So I'll take 2022 and 2024. I can come up here to SBAS filters. I'm going to change the start date here. I can just click on these years, and we're going to say 2022, January 1, 2, and I'll say 2024, January 1. So I'll take 2 years of data. No overlap threshold, that's fine. All right, so now if I zoom out a little bit, you can now see all the interferograms, all those blue lines are gone except for from 2022 to 2024. I'm also going to reduce the perpendicular baseline. The perpendicular baseline, the larger that it is, the higher possibility that you introduce some errors or some noise. So I'm going to go ahead and take that down to, let's say, about, I'm going to go maybe 200 meters. It's a little bit too much. There we go. Close enough. All right, so now you can see some of those blue lines disappeared. Not too many, actually, because it's a pretty good network. Not too large of perpendicular baselines. So now I've got these interferograms, and it turns out that's 142 pairs. And what I'm going to do now is I'm going to request that ASF process these 142 pairs for me. So I've got the one selected. You can also add a custom pair. For example, I could say, I want to add a custom pair. I'm going to click that plus, and I'm going to click the 2 dates that I want to make those pairs for. So maybe I want to connect these 2 dates for some reason, and I can say that. Maybe I want to connect these 2 dates, so I can come over here. There we go. And you can see as I'm doing this, the number of pairs is going up. So over here, it's now 144 pairs. And let's just say, for example, that I wanted to do a relatively long pair. Maybe I wanted to try to connect these 2. Now, of course, the longer your temporal baseline, here's your temporal baseline here. It's the number of days. So I've limited the temporal baseline to 36 days because the longer your temporal baseline is, the more likely you'll have decorrelation. So decorrelation is a degradation of the quality of the interferogram, and you won't be able to use decorrelated pixels to do time series. So in general, I want my times to be shorter. However, a longer interferogram can actually give you more information about deformation happening because the longer your temporal baseline is, the more deformation that could have happened during that time. So there's this trade-off that we have between longer time periods between your acquisition dates results in potentially measuring more of the deformation that's happening and possibly also decorrelating, so lower quality, so you can't actually see the deformation that you've had in that time period. So you have to do this trade-off. And so what I'm going to do is I'm going to keep my temporal baseline short for the most part, 36 days or less, but maybe I'll add in a couple of pairs that are a little bit longer. So maybe I'll try doing these 2 pairs, and maybe I'll try doing, connecting this one with one over here. Go ahead and do that. And you can experiment, of course, with this. Of course, each pair that you add is going to be another pair that gets processed. And so that will take extra time, extra processing time, all of that. And if they're bad quality, you don't want to do that. So you don't want to overtake long pairs, custom pairs. But you can add a few in there, and that may or may not help you when you're doing your analysis. Depends on how decorrelated it is. Okay, so now I'm happy with my pairs. I've got some good pairs there, and I've got this whole list of interferograms now, 147 interferograms that I'd like to process to do time series. Well, ASF doesn't do the time series processing for you, but it allows you to process these and get actually INSAR results. So we can come up here to the On Demand button, select that. We can do INSAR gamma, and we're going to add 147 SLC pairs, which is going to take 1,470 credits. So each full INSAR frame that you do will be roughly 10 credits of ASF processing time, and you actually can process 10,000 credits on ASF every month for free. So just by signing up for an account, you get access to 10,000 credits of processing power from ASF every month. So obviously, if you're doing very large areas and doing long time periods, that's going to add up and you're going to need to do a different solution. But for doing smaller areas, smaller time periods like this is actually a really great product, a really great service that ASF provides for folks to use up to 10,000 credits. So I'm well within my 10,000 credits. I'm going to go ahead and add those to my queue. All right, now I just realized that I think my on-demand queue had some other jobs in it from before. I'm going to clear out that queue. So now my queue is empty. I'm going to come back over here and add these again. I think I had another job that was previously in there. So now I can go to my on-demand queue, and you can see some information at the top. We'll look at that in a second. And here's all the pairs that are going to be processed. 147 jobs, 1,470 credits. Okay, so now there's some processing options. And what we want to do is we want to set these processing options so that we have the information that we need when it comes time to do the processing in our time series processor. The number of looks is, you got two options there, and you'll notice that if you select fewer looks, it's more credits. So I'm just going to leave it at the default for now. Phase filter is as a phase filter parameter. Larger values result in stronger filtering. This is something that you could play around with if you are doing a lot of different processing jobs. For now, I'll just leave it as the default, and that's probably going to be good for most of your applications. I'm not going to apply a water mask, but I'm going to include the DEM for each frame and the incidence angle, the look vectors. I'm going to go ahead and include the displacement maps. That basically takes the unwrapped phase. So what it's going to do, ASF is going to process the interferograms, and then it's going to unwrap the interferograms, and it's going to provide you the unwrapped interferograms. And that's actually what we need to do time series processing. So we can actually convert those directly to displacements. What's the difference between unwrapped phase and displacement? Well, unwrapped phase is in units of phase, and so that's something that we need to convert over to meters or millimeters or something like that. And that's what these displacement maps are. So these will be actual units of meters or millimeters. And again, this will be line of sight displacements relative to our satellite line of sight, which is why we need the look vectors and the incidence angle so that we can calculate what the actual deformation is. We'll get the line of sight deformation from the displacement map. In order to know what the real deformation is, we need that information about the look vectors and incidence angle. We can also ask for the wrap phase if we want. I don't need that right now. That's just going to be the image of the wrap phase, and I don't need that for time series processing, just the unwrapped phase. And so that's all I need. So I've set my options. There's all my jobs ready to go. And I can say submit 147 jobs to ASF for processing. I'll go ahead and click that. I'm going to give my project a name. You can see I've got a couple of different projects here. I'll call this a class test in SAR Gamma. Submit 147 jobs. Oh, there we go. 147 jobs submitted. So now if I go to my on-demand queue, you'll see my queue is empty because I've submitted all the jobs. And I can come back here and go to my submitted products, and it will show me the ones that are being processed. So here are all the jobs now that I've just submitted, and they're now pending, waiting for the processing to happen. If you submit jobs to ASF, it will typically take about a day, maybe a couple of days to get the processing finished. So you'll see, and you see I've done a lot of processing before, a couple of thousand products. So these jobs are waiting to be processed, and you'll get an email notification. When you sign up for an account, you'll have to give your email. You'll get an email notification when that processing has finished, and you'll be able to come back to this very spot and add these jobs to your downloads and then download them. So we'll take a pause for a moment, and when these jobs have processed in a few hours or a day, then we'll come back and finish the video. So I've got all the processing done. You can see here I've logged back into ASF's website, come to On Demand, and gone to Submitted Products. Now, when you look over here, before you saw the queue word saying that they were queued to be processed, now I can go through and click on these products, and they'll actually show up in my browser And it's kind of interesting to kind of go through and see what the different interferograms look like on different days. You can see there's some really long wavelength process, maybe a weather front or maybe a ionospheric disturbance. Different ones you can go through again and just sort of see what they look like. So now that I've got all my products processed, I'm going to come here to Q and I'm going to say add my results to downloads. I can come up here to downloads, and now there's a couple of different options. One is to do a direct download all, and that's a possibility that you can try out. I usually don't do that. I will usually download a Python script, and let me just quickly show you how that works. I'll go ahead and download that, and then I'll open that up. And here's what this looks like. And this is nice because this is actually a Python script that I don't have to write. It's already been written. Everything works. And it's got the list of all the different files that I want to download. And then what I'll do is I'm on a Mac, so I'll open up a terminal. I'll come here to my directory, and I'll need to have Python installed. But once I do that, then I can simply type in Python and then put the name of the script and hit enter. Now, the first time that you do this, it's going to ask for your username and password. And that username and password is going to be the same one that you use to log on to the ASF website. Once you've put that in, then it should come up and start downloading. And you can see I've already got some of these files downloaded. So it says that one's already exists. I've already downloaded that file. And then it's continuing to download. Once you've downloaded, if you have any problems with the download, you can come back and always rerun the download script, and it will download the files that are missing from the list. So if you have an error or an internet outage during your downloading, you have to stop it and come back. That's an easy way to do that. So this is a good way to do this if you have a Mac or a Linux machine and you can use Python, or if you're using Python on your laptop computer. Now, if you're not using Python, or not comfortable using that on your own computer, then again, you can always come back down here and download all the products directly. This is experimental, as you can see there, but it should work, and I've done this before and it worked just fine. However, it will take some time to download. In this case, I've got quite a few files, so it'll take some time to download all those files. Individually, the files are not super large, 340 megabytes or so, but if you have a slow internet connection, that could take a while, so just keep that in mind. The other thing that you'll want to just check once you've got the files downloaded is that all the files are the same size. So here now I've opened up the folder, the St. Louis class test folder, where I'm downloading my products, and I can click on these different products here. And you can see that they're all about 350 megabytes in size. If I had a file which was a lot smaller, a lot different size, that probably means that I've got a failed download. I should delete that file and either re-download that individual one or rerun my script and re-download that file. Okay, so now I've got my files downloaded. What's the next thing to do? All right, so once you've got your products downloaded, the next step is to unzip the products into our working directory. And I've already done this step. You can actually see them listed here. But before I jump into that, I want to just take a couple of minutes and talk about how to do the next steps. So the next steps are going to be similar to what we did in Google Colab, but you'll probably want to do them on your own laptop, just because it's easier working with the data there than trying to get the data into Google Colab and all of that. But you could try doing that as well. That would be fine. You could, in that case, put the data into your Google Drive and then open Colab and refer to that Google Drive. And the steps will essentially be the same as what I'm going to show you here. But you can also do this on your computer. The easiest way probably to do this is to use what's called a Jupyter Notebook. And this is very similar to what we've done in Google Colab, a notebook kind of interface. You can install Jupyter for Windows and Macintosh, and I'll put links to those things in the notes to this video. Once you've got Jupyter installed, I'm going to have a link to this notebook also in the notes to the video. And you can open this right up and follow with the steps, just like I'm going to do right now. So here we have all of our products, and you can see I've got all the downloaded products here. And notice that I've unzipped these. So when you download the products, they're going to be zip files, and you'll need to go through and unzip them. And you can do this, of course, on any platform. Unzip the folders into folders. And actually, I'll come over here for a second. Now you can see here I've got my St. Louis class test. I've got my different folders here, and inside each folder is a list of files, and I'll just maximize those files here. Lots of different files in each one of these folders, and this is going to be included for each one of the folders that you download. So quite a few files. The files that are going to be of most interest to us are going to be the unwrapped phase files, and those are going to be right here. So unwrapped phase, unw phase.tiff. That's our unwrapped phase files. You could also consider using your displacement TIFF file, your LOS displacement, LOS disp. That's going to be the same thing as your phase, but just converted to meters or millimeters. You've got a DEM, dem.tiff, that's your DEM file. Core.tiff, that's going to be your coherence file. And you've got a few others. You got your amplitude file, your angles. These are going to be your look vector files. Vertical displacement file, that's a file that ASF actually calculates, assuming that all the displacement is vertical. And of course, it's not accounting for noise and things like that. So I wouldn't trust this vertical displacement file too much, but they do provide it there if you wanted to see it. Also a water mask. And that's, of course, if you selected those options on the ASF processing that we showed earlier in the video. And a number of images also as well. So you can sort of look at these images and see what some of these interferograms look like. So here's one particular interferogram. Okay, so now that we've got our files downloaded, we've got them unzipped. Now the next step is to process them. And there's really two steps that we need to go through. The first step is to take all these folders, all these interferograms that we've got here, and we've got 294 interferograms in this test case that I'm running for you all. The first step that we need to do is actually to resample the interferograms. It turns out when we download these from ASF, they can be in different sizes. Some of them will have extra pixels or rows in the image, and so we need to put all of these interferograms into the same size of an image so that we can work with them all in the same reference frame. So they're all geocoded files, but we need to take the same area, the same region, and make sure that that region is exactly the region that each one of the interferograms is covering. And that's what this run resampling code is doing. It's going to take the current directory. This is the Python call to get the current directory. And right now I'm running this in my working directory here where all these folders are. And so it's going to take this, it's going to search through all these folders, and it's going to find the images that you need, the TIFF files that are going to be used later on for processing, and it's going to resample those. You don't need to worry too much about this. I'll have this, this function will be provided when I put that link on the video notes. You'll be able to find that function and use it, just like we used the make TS. And that's actually our second step. So once we have everything in the same reference frame, everything is the same size, and we can work with all the different interferograms together, then we can use our make TS function like we did in Lab 4. And so here I'm just grabbing the interferogram list. I'm grabbing the list of coherence files in this case. I found 294 interferograms. And then this is all the same processing that we did in the INSAR lab. And I'll have a link to the INSAR lab. If you're watching this video and you haven't done that lab yet, I'll have a link to that lab in the notes to the video. Okay, so we have these interferograms, they're a particular size, and of course all the interferograms now are this size since we've run that resampling program. We can do our dereferencing, we can make some plots, calculate time series, convert those to meters, and look at the velocity. And I believe I've already run all of this actually, so we can look at the shape. Yep, there we go. And our velocity now is the same shape as our interferograms are, of course. So this is exactly the same as the workflow that we went through with the INSAR lab. So the key bit here is going to be getting Jupyter installed, being able to run this notebook, or, as I said, uploading the files to Google Drive if you want to go that route. I would say the more files that you have, the more challenging it will be to do this with Colab, but it can still be done as long as you don't have too many files that you run out of memory. On my laptop, I've got a good bit of memory, and so it works really well to just run this on my laptop. And I think I've got, well, as you can see, I've got 294 interferograms, and however many dates, I forget how many dates are in this stack of interferograms, but probably about 100 days or so. Okay, so this is now what you need. Get Jupyter installed, download your files from ASF, unzip them, and then run the resampling program which again will be you'll be able to access that from the link that I put in the notes to the video. That's the resampling program. And then here's our MakeTS program that we've already used in the INSAR lab. And again, if you haven't looked at that lab, I'll have links to that in the video notes as well. We run through that, we get our velocities. From there, you can look at individual pixel time series. That's a good thing to do. You can plot the images for each date. All of those kinds of things can be done once you have your final time series. And from here, this is where your creativity and scientific curiosity comes into play. This is the processing to get the interferograms and to get the time series from those interferograms. But then what you do with it, then what kind of discoveries you can make from the observations, that's going to be up to you to show some curiosity, do some exploratory plotting, do some exploratory analysis, maybe calculate some statistics, maybe look at trends, whatever it takes, you can do that. Of course, you've already got the velocity function here, so you can calculate velocities. You might also look at how the cumulative change in the time series through time, anything like that could be interesting things to do with this INSAR data. So I'll leave it up to you to use your creativity and figure out how to do your own analysis. Check out these notebooks. I'll have, again, the links in the video notes, and good luck with the processing.